Hi there and welcome to tutorial 16 on mutually exclusive and independent events, and this is for the Edexcel S1 A-level module. It is applicable to most other exam boards, and as always, if you're looking for further help with your studies, do check out youtube.com/Mr. Arnold's Maths. Okay, so let's talk about mutually exclusive events. Now, events that have no outcomes in common are said to be mutually exclusive. So if we think of our classic Venn diagram we've been using so far, um, when events have no outcomes in common, that essentially means that there is no intersection for the two regions. For example, rolling a die and tossing a coin. When we roll a die, if A was the event that we roll a die, we could have a 1, a 2, a 3, a 4, a 5, or a 6. And if we toss a coin, the outcomes are we could get heads or tails. So as you can clearly see that these two events have no outcomes in common, they're said to be mutually exclusive. Now, there's a really important feature that arises because of this. Because there is no intersection, that essentially means that the probability of A intersection B is equal to 0. So if we think about this feature and then apply it to the addition rule, if we remember the addition rule, which was that the probability of A union B equals the probability of A plus the probability of B minus the probability of A intersection B. So if we apply this fact to the addition rule, that means when we have two mutually exclusive events, the probability of A union B is simply just the probability of A plus the probability of B. And that's because A intersection B is 0. So these are our two tests for mutually exclusive events. Either we prove that the probability of A intersection B is 0, or we prove that the probability of A union B is simply the probability of A plus the probability of B. If you can show either of these, that means that the two events are mutually exclusive. Okay, so let's take a look at an example. We've got two events, A and B, and they are mutually exclusive. We're told the probability of A is 0.3 and the probability of B is 0.4. And we're asked to find these probabilities. So as always, we're going to start by filling in our Venn diagram. Probability of A is 0.3, so that goes in there. Probability of B is 0.4. That means that everything outside the two circles must be 0.3. And just checking that they all add up to 1. 0.3, 0.3, 0.4 does indeed add up to 1. So our diagram is correct. Okay, let's answer the questions now. The probability of A union B. Well, remembering from before, the probability of A union B when we've got two mutually exclusive events is simply the probability of A plus the probability of B. So I'm just going to add these two regions together. 0.3 and 0.4 is 0.7. What about A intersection B complement? So A intersection B complement is everything that's in A that is not in B. Well, it's quite obvious that it must be 0.3. The probability of A intersection B complement when we're dealing with mutually exclusive events is simply just going to be the probability of A. And if I want the probability of A intersection or A complement intersection B complement, that's just everything outside the two circular regions. That must be 0.3. Okay, fairly straightforward example there. Time for you to have a go. So very similar example here. Pause the video and try the question. Okay, hopefully you've had a go at that. Here are the solutions. We simply filled in what A was and what B was. That gave us the outside, and then we answered the probabilities. A complement intersection B, everything that's in B that's not in A, so simply just the probability of B. A union B, add the two probabilities together from A and B, and A complement intersection B complement 0.25, everything that's outside the two circular regions. Okay, let's move on to independence. So if an outcome of an event does not affect the other, then they're considered to be independent. Okay, this is really important. So let's have a look at a couple of examples just to kind of get the idea across. Suppose we have a jar with 4 red and 7 blue beads, and we're gonna take a bead out at random, and in this instance we're not going to replace it. So I'm going to fill in the tree diagram. If I choose a red, it's going to be the probability is going to be 4 over 11. There's 4 reds and 11 beads in counters, 11 beads in total, and with regards to the blue, there is a probability of 7 out of 11. Now, if I don't replace the bead and then I select another one, the probability of choosing a red on the second occasion is going to be 3 over 10, and a blue will be 7 over 10, because there's still 7 blue beads left. If I choose a blue and then I choose again and I get a red, it's the probability that that happens is 4 out of 10, and the probability that I choose a blue bead after I've chosen a blue bead is 6 out of 10. Now here's the catch. We have to be able to fill in our diagram correctly, okay? So this first part is simply the probability that it's red, and this part is simply the probability that it's blue. Now this branch here actually represents the probability that it's red given that I chose a red the first time, and here it's the probability that it's blue given that I chose a red bead. Over here, this is the probability that it's red given that I chose a blue bead first, and this is the probability that it's blue given that I chose a blue bead first. And if we multiply across the branches, as always, we get 12 over 110. We get 28 over 110. 28 over 110, and 42 over 110. And at the end of these branches, that actually represents the probability of red intersection blue. Sorry, red intersection red, should I say. Red intersection red. Probability of red intersection blue. Probability of blue intersection red, and the probability of blue intersection blue. Right, now let's have a look at what happens to our tree diagram if we don't replace, or sorry, if we do replace. So in the probability that I choose a red in the first go is 4 out of 11, and blue will be 7 out of 11. Now I am going to replace that red bead, and then I'm going to choose again. So if I get a red bead again, the probability is still 4 out of 11 because I've put the first red bead back into the bag. Blue will be 7 out of 11. This is still 4 out of 11, and this is still 7 out of 11. But let's see what it does to the meaning of these branches. Now this is still the probability that we choose red, and this is still the probability that we choose blue. This is the probability that we choose red given that we've chosen red. probability that we chose blue given that we chose red, probability that we choose red given that we chose a blue, and the probability that we chose blue given that we chose a blue. Again, we can multiply across our branches. 16 over 121, 28 over 121, 28 over 121, and 49 over 121. But what do we notice? We notice that when we do replace the bead, the probability that we chose red is the same as the probability that I chose red given I chose a red. So what we can say is that if the probability of choosing red given I chose a blue, so let's actually look at this branch here. The probability that I chose a red given I chose a blue is the same as if it was the probability that I simply chose a red. That means that these events are independent. So the two events are independent because it doesn't matter what happens in the first instance. It has no effect on what happens afterwards. So the probability that I chose red given I chose a blue is the exact same. You'll notice it's the exact same as if it was the probability that I chose red. So the two events are independent. Let's just formalize that again. So if the probability that I choose red given I chose blue is the same as the probability that I chose red, that means they're independent. Shocking spelling today. Let's just shorten it, save time. So they're independent. So the multiplication rule then is looks like this. We know that the multiplication rule says that the probability of A given B equals the probability of A intersection B divided by the probability of B. That's our multiplication rule from before. But if red given blue is the probability of red, we can apply that to our A and B. So if they're independent, then the probability of A given B is the same as the probability of A. That has to be the same if they're independent. So that's going to equal the probability of A intersection B divided by the probability of B. And if we cross multiply, that means the probability of A intersection B must equal the probability of A multiplied by the probability of B. So the probability of A intersection B equals the probability of A times by the probability of B. And that's if they're independent. Okay, and that's a test for independence. If you want to show two events are independent, you multiply the probabilities together. If that equals the intersection, then the two events are independent. And if you think back to this, probability of R multiplied by the probability of R given R is in fact the probability of R intersection R, and this is going to be the probability of R intersection blue B, probability of blue intersection R, and the probability of blue intersection blue. So this is our test for independence. Okay, let's take a look at an example. So suppose we've got two events, A and B. They're independent, and I'm told the probability of A is a third and the probability of B is 1/5, and we're asked to find these probabilities. Well, because they're independent, I know that the intersection, the probability of A intersection B, will equal the probability of A multiplied by the probability of B. So if I want this intersection, I simply multiply the probabilities together. 1/3 times 1/5 is 1/15. So if that's 1/15 and the total of A must be 5/15, that's the same as 5/15, that means this region here must be 4/15. This is going to be the same as 3/15, so that means the remaining part must be 2/15. And then adding them all together, 4 and 1 is 5, 6, 7, 7/15 in this region. That means that 8/15 must be on the outside. So let's work out our answers here. A intersection B is 1/15, this region here. A intersection B complement, so everything that's in A that's not in B is going to be 4/15. And A complement intersection B complement, everything that's not in A or B, is 8/15. Okay, time for you to have a go, so pause the video now and see if you can work out the answer to this one. Okay, hopefully you've had a go at that. Here are the solutions. So we got the intersection by multiplying the two probabilities together. Then we worked out the balance. That's 5/35, and that's 7/35. Fill in our diagram, and then it's fairly straightforward to answer the questions. Okay, we've got another example here. So we've got two dice are rolled. One is red, one is blue. So I'm going to call the first die the red one, and the second die can be the blue one. Okay, A is the event. The red die shows a 3. B is the event. The blue die shows a 3. C is the event. The sum of the outcomes is 5, and B is the event. The outcomes of each die is the same. Show that A and B are independent. So let's go to our diagram first and just use the diagrams to help us. So A, the event that the red die shows a 3. So these are all the ways that the red die can show a 3. And B is the event the blue die shows a 3. So we need to show that these are show that A and B are independent. And we see because they overlap, they're actually independent. But let me just prove why. We know that the probability of A happening is, let's see, A is the red die shows a 3, so that's 1 out of 6. 1 out of 6. The probability of B is also 1 out of 6. What's the probability of, if they're independent, that means the probability of A intersection B must equal the probability of A multiplied by the probability of B. And that would give us 1/6 times 1/6, which is 1/36. So if we look at it, A and B are independent. Is that the case? Well, what's the probability that we get a 3 on the red and a 3 on the blue? It's 1 out of 36. Therefore, the two must be independent, and you can clearly see that because the two highlighted areas overlap at one spot. There's one spot out of 36, so it's 1 out of 36. So because this is true, that means that it's independent. What about showing that C and D are mutually exclusive? Again, if C is the sum of the outcomes is a 5, so these are all the ways we can get a 5. D is the event the outcome of each die is the same. So we could have a 1 and a 1, 2 and 2, 3 and 3, 4 and 4, 5 and 5, 6 and 6. So that's um, the outcome of each die being the same. Now, if we want to show that C and D are mutually exclusive, we can actually see it here in the diagram. Because they don't actually cross at any common place, that means there's no outcomes in common. So absolutely no outcomes in common. In other words, that the probability of A intersection B equals 0. So the probability of A and B happening at the same time is 0. And if we think about it, there's absolutely no way to get a score of 5 if you roll 2 die and have both die with the same number, because if we add two numbers that are the same, we're always going to get an even number. 5 is an odd number, so it cannot happen. Right, okay, let's move on. So another example, we got a football team, and in a season they play 40 games in different conditions with the following results displayed in a table. So if we let S be the event we have sunny weather, W be the event the team wins, D be the event the team draws, and L be the event the team loses. We need to first of all find what is the probability that it's sunny. Well, in the season, if we've got 12 sunny, not 12 sunny games, we've got 23 sunny games out of 40 sunny games. That means the probability that it's sunny is 23 out of 40. What about the probability of S intersection D? So the probability that it's sunny and they draw. Well, going to our diagram, we can see this is the number of times it was sunny and they drew. So the probability that it's sunny and they draw is 6 out of the 40 matches. What about the probability that they draw given that it's sunny? And this is a good chance to use our shrunken sample space method. So given that it's sunny, which is here, what's the probability that they draw? Well, that means we have 6 out of 23 opportunities. There was 23 times it rained and 6 times they drew. So the probability that they draw given it's sunny is 6 over 23. There is another method to do this. See if you can work out how to do it. I'm going to save a little bit of time and just move on to the last part. So we want to know, are D and S independent? Well, the probability of D is 8 out of 40. So the probability that they draw is 8 out of 40. So I need to check what the probability of that the probability of D, it should be the same as the probability that D given S. If we think back to our tree diagrams from earlier. Yeah, if they're independent, that means the probability that they draw is going to be the same as the probability they draw given it's sunny. And we can clearly see that the probability of D is 8 over 40 and the probability of D given S is 6 over 23. They are not equal. That means they're not independent. So they're not independent. Okay, no more questions for you to try, but you should now be able to complete exercises 5F and 5G. That's it for this video. Hopefully you found it useful. I'll be back again soon with a new video, so best luck with the revision and I'll talk to you again sometime.